Okay, so in this one, this is for method students who are finishing off the rest of the course. What we're going to do is finish the chapter 17, the final chapter of the entire course, well, chapter 17 in the Cambridge textbook anyway, on sample proportions. What I'm going to do is hopefully very, very quickly take you through the entirety of the topic and prove that it's actually not all that much different from the stuff you've already done in chapters 14, 15, and 16. That being binomial distributions, continuous distributions, and then normal distributions. First, have to just break down in 17a, we're just interested in what is a population, what is a sample, and then what is a sample and population proportion. So to explain that, what we can do is if we take, for example, all of Australia, right? And this is my best attempt at drawing in Australia here. So the entire population of Australia is going to be 25 million people. So what we'll do is we'll call this capital N. So this is our population size, right? 25 million. And if, for example, we're interested in looking at, say, the number of people, or we're interested in the proportion of people who have type O blood, right? So we have type O blood. Then we do know already statistically that 49% of all Australians have type O blood. And so what this means is that the proportion of the entire population, so the population proportion P, is going to be 49%, or we'll express it as 0.49, like that. Now, if we were interested in understanding the distribution of that particular statistic within a smaller sample, we're not going to sample the entire population because that would be tedious and it would take too long, right? So what we'll do is we'll sample just a small part of it. Now, I won't go into detail, but I mean, obviously if you're sampling, there's different methods. Some of them are more or less biased than others. If we were just to pick, for example, Victorians, just because it's convenient, then we'd be leaving out the representation from other states and other regions and subpopulations within that population. So we might have some bias in our sample. The best way to do it is to randomly sample, meaning that you allocate people into the sample. So a good way to do it is give everyone a number, put it in a hat, randomly select the number. For simplicity, let's just say we take a small sample here, and we're going to have 100 Australians in that, 100 people. So now on our sample side, we have a sample size of little n, and that's going to be 100. And then we would have a proportion of people that are type O blood in that group as well. And we're going to call that P hat. That's our sample proportion of type O blood. Now, realistically, it won't necessarily be exactly 0.49, even though that's what it is in the population, because there may be some statistical error, chance events, or bias in our sample. So we might find that it is 0.3 instead, a little bit lower than average. But either way, these would then be the distributions of each, although what we're interested in is how does that P hat distribute itself within a sample, and then how does it respond when the sample size changes as well. So the next thing that we can think about is, well, what is the expected P hat value? So this is going to be the mean. So if I was to pick a random sample of Australians and then ask you what fraction of them do you think would have type O blood, without any other knowledge, you have to rely on the population proportion. And so you would say 0.49. And so that explains why the expected value of P hat, the mean, is going to be equal to the population proportion, right? So we expect that the sample proportion will be equal to that in the population. The second one, we have a formula. So the standard deviation of P hat is given by the square root of P times 1 minus P, or the complement, divided by the sample size, and we square root that. And so we've got these two formulas which will help us now define our distribution. So then the next thing is, how does it distribute itself? So if our sample size is less than 100, then it's going to distribute itself binomially, right? So this will be a binomial distribution. And therefore we can say that P hat is binomially distributed, and it'll have a sample size of n and a probability of success being the population proportion, just like we did in chapter 14 in binomial distributions. If, however, the sample size is greater than or equal to 100, and some people argue over what that limit is, 100 seems to work quite well, then we assume that now it's going to be so large that it's effectively normally distributed at this point. And so now we're going to say that p hat is approximately normally distributed with a mean value and a standard deviation, or really a variance we're supposed to say. And the mean is going to be p, because that's the expected value. Don't forget that is mu. And then the sigma, which is the standard deviation, is this. So really the sigma squared would be this squared, which would actually cancel out like that. And so what we'll actually see here is whatever p times 1 minus p, oh, that's terrible. So we'll see whatever p times 1 minus p over n is going to be, that will be our variance. And then that fully defines p hat if it were to be normally distributed. So if we consider it to be binomially distributed first, let's say that we take a sample, but this time we're not going to do 100 because it would be far too large, and that's where it would be on the cusp of becoming normally distributed. Let's say we have a sample of just 5 people, right? The population proportion of type O blood is still 0.49. And what we're going to be interested in is the variable x is going to be equal to the number of people in our sample with type O blood, right? So the number of type O people. But what we're more interested in is the p hat value. And that's going to be the proportion that x represents. So that is the value of x divided by the sample size. What fraction of those 5 people are actually type O blood? And so we can basically approach this just like a binomial distribution with x, except our statistic that we're more interested in is going to actually be the p hat value. So normally we would put here x, and then we would put the probability of x equaling x, and we would create a probability distribution table. And so we could have 0 people in our sample with type O, we could have 1, we could have 2, we could have 3, we could have 4, or all 5 of them, right? And then we would do the probabilities. And if we were to do the first one, for example, we'd use the Bernoulli sequence, and it'd be 5 choose none times by the probability of success, so p, 0.49, to the power of 0, and the remainder 0.51 to the power of 5 minus 0, or 5. And then we would keep calculating that and fill in our table. The only thing that's different this time is we don't really care so much about what x is, so we're more interested in what is p hat that relates to that. So here it would be 0 out of 5, or 0. This would be 1 out of 5, 2 out of 5, 3 out of 5, and 4 out of 5, and then finally 1. So be careful, because obviously a lot of them are fractions. They're not probabilities. They are the statistic that we're more interested in. You'll notice though that the probability of each p hat value won't be any different. So what that also means is that the probability of x equaling x is the exact same thing as the probability of p hat equaling p hat. So if you're looking for the probability of p hat equaling 1/5, that's the same as asking what's the probability of x equaling 1, right? And it would be calculated exactly the same. And so therefore, if they ask us something like what's the probability of p hat being greater than say 0.5, we can see here that this is 0.4, this is 0.6. So basically all the probabilities of these 3 added together. But we can also, if you prefer, you can think of it as just, well, that's saying the same thing as what's the probability of x being greater than half of my sample, which is 2.5. And so really, because this is discrete, that would be the probability of x equaling 3 plus the probability of x equaling 4 plus the probability of x equaling 5, like that. There we go. So that's how we can do binomial distributions. You could also do binom PDF and binom CDF on the calculator as well, and it works exactly the same way. Then if it were to be normally distributed, then we can either use the approximation of the curve with all of the percentages between each of the z-scores, or we can use the norm CDF function on the calculator as well. So if x is normally distributed, therefore p hat would be normally distributed, and it would have a mean of p and a sigma of p times 1 minus p on n. So again, let's do that, right? So if we do the p hat values of people with type O blood, then that would be 0.49 for the mean, and here it would be 0.49 times 0.51 divided by our sample size. Let's go with, actually not 5, let's go with a sample size of 100 this time to make it just normally distributed. And there's our p hat distribution, like that. And so now if we're asked what's the probability that say 30% of our sample has typo blood, right, or 30% or more, then that would be the probability that p hat is greater than or equal to 0.3. And we can do that. So we can just use the norm CDF function. We'd put in our limits. So our lower bound would be 0.3. Our upper bound would be 1, because that's the highest that p hat can go. And then our mu would be 0.49. And then our sigma, keep in mind, even though we write sigma squared here, we do put the sigma into the actual calculator, which is going to be square root of 0.49 times 0.51, I'll just squeeze that in there, over 200. And then that would spit out our probability, just like that. If you didn't like it that way though, you can just translate it and say, well, that's the same thing as the probability of x being greater than 30, i.e. 30% of the sample size. And then you could do the exact same thing, and then your mu this time would be what is 0.49 times the sample size. So the lower bound would be 30 people, right? Greater than or equals to. The upper bound would be all 100. The mu would be 49, right? So if the population proportion is 49%, we expect that 49 out of our 100 will actually have typo blood. And the sigma, which over here, it won't be these numbers, it'll be the sigma of the actual sample. And so that would be this times the sample size. And you'll notice in each case, they're all times the sample size. And that just brings us back to the idea that if p hat is equal to x over n, then that means that x is equal to p hat times n. So if you want to convert from p hat values to x values and use the x distribution instead, then you just multiply everything by the sample size. And then finally what we have is confidence intervals. So in a confidence interval, we're just trying to work out what range of p hat values or any statistic value do we have a 95% assuredness or 95% confidence that the statistic will lie within that range within a certain sample. So I'll switch colors here. So we use that same thing from normal distributions. The 95% confidence interval was always written as the mu plus or minus 2 standard deviations. What we do in this case is we go a little bit more specific. 2 is actually an approximation, which means that whole graph is actually a slight approximation. And instead we use the true variance, which is 1.96, right? Instead of 2. 2 is just rounded. And then we multiply that by the standard deviation, which is, as we know for p hat, is p 1 minus p on n square root. And remember the mu as well is actually not mu, it's written as p, like that. And so this gives us our full confidence interval. So we can say that p hat, we can be 95% sure that p hat will be an element of somewhere between p minus 1.96 times the square root of p times 1 minus p over n. Is that pain to write? And then is less than or equal to p hat, is less than or equal to, and then p plus 1.96 times the standard deviation. And there's our 95% confidence interval. And so what we can also find is that there's a margin of error called m, and that is going to be 1.96 times the square root of p times 1 minus p over n. And this is how much it varies either side of the mean. And so our margin of error is just going to be this here. And we can visualize that because if we were to graph this out, remember that p hat is assumed to be normally distributed, then what we're saying is that if this is the mean, p, we're fluctuating by m either side of it, and this is creating our confidence interval. And so this is considered our margin of error. As your sample size goes up, your margin of error goes down, right? And you can see that there's an inverse squared relationship right here between the margin of error and the sample size. If we kind of get rid of everything else, holding p constant, then we can say that m is proportional to anything that's constant becomes a 1 here. All the maths apply. So the 1.96 becomes a 1 because that's a constant. All of this, p and 1 minus p, is not going to change if we're still talking about typo blood. So that all becomes 1, and then it's over n. So we can see here, we could split this like this, and we can see that there is an inverse proportionality, an inverse square root proportionality between the margin of error and the sample size. So as you increase the sample size, you will decrease the margin of error, and that will actually make your data more accurate, which also explains why in something like a science experiment, larger the trial number, the more accurate and reliable your data is, because you're actually lowering your margin of error based on how that statistic is distributing itself. And there we go. That is everything in chapter 17. You can see that it links across binomial and normal distributions. You won't see continuous distributions used for p hat. It can be done, but they pretty much stick with binomial and normal. And really the content is actually exactly the same. It's just instead of using x values, you're using p hat values. If you don't feel comfortable with it, you can always just make the statement that it's equivalent to a particular x probability, and just convert everything over by multiplying by n, and then you're good to go again. All right, cool. That's everything there. If you enjoyed this video, if you took something out of it, please like it, please subscribe and tell your friends to also subscribe. So I'm gonna keep doing these videos as we run to the exams as well. I'm focusing mostly on year 12 subjects. As we run to the exams, I'll continue to make videos that go backwards towards the earlier part of the year where I wasn't making videos, and it can be based on request as well. If there's a need for something, then I will make a video and emphasize that, because realistically I won't be able to get through the entire course before exam time, but we want to keep them nice and simple and bite-sized each time, so let me know. All right, bye-bye.